Now that we understand ways that we can find an empirical formula, we're going to look now at how to, from an empirical formula, how can we determine the actual molecular formula. So remember, the empirical formula is the simplest ratio of those ingredients that make up the whole compound. When we talked about sugar, for example, that was an example of where the empirical formula we divided by 6. Remember, to get the ratio between the atoms in the molecule. But now we want to actually find the whole entire thing. And we can do this with an instrument called a mass spectrometer. And this is a general description of how that works. And we're basically, as described in the name, we're going to be able to determine the mass of what we're looking at. So here you can see this example. We have chlorine gas, Cl2, that is a divalent molecule. So there are two atoms attached to each other. You can see here. And this is representing two different isotopes. Remember, we talked about isotopes that would be defined by the number of neutrons in the atom. So this is a heavy element of chlorine. It has the atomic mass of 37 versus a lighter version with 35. How this works is we would inject this into a sample port, and that has a flow of gas. So you usually have some type of carrier gas that's not going to be interacting with this. Typically, helium is used because it is an inert gas. That's expensive. The one that we have on campus, I converted it into hydrogen gas, where even if it does break apart, it's going to just help push stuff through, but it's not going to influence the detection afterwards. So what we do is we put this in here, and this stuff is constantly flowing with this carrier gas, which isn't shown here. And you can see these different molecules get ripped apart through this ionization. So we put through high energy electrons through here, and what they do is they attach and they blow up this molecular bond. After the ionization event, you can see that these have charges, so they're ripped apart into two different atoms that have a charged state. And they're accelerated through this ion beam. There are magnets that are going to generate and put these into a line as they go through this tube. And a magnetic field is applied to these positively charged ions. And that's going to deflect them. So we're going to have a negative magnetic field. And the heavier thing is actually going to be deflected less than the lighter thing. And that kind of should make sense if you're thinking about if you would blow on, let's say you had a golf ball hanging off the ceiling in your garage versus a bowling ball. If you blew on the golf ball, it's going to move a lot more than the bowling ball is, or a tennis ball, for example. That's going to move a lot more. So that's kind of what this magnetic field is happening. It's going to push things down more if it's lighter. And then depending on where that ion hits on this detector, that's going to dictate the size of it. So the higher up here is going to be a higher mass to charge. So we're talking about the mass and the charge because it's a +1, but sometimes you might have a +2 or +3, and that's also going to dictate where this thing happens, flows, right? So if it's a +2 charge, it's going to be deflected even more because it's a heavier positive charge in there, or a greater positive charge. So the mass to charge ratio, if it's a single charged element, you're going to be able to determine the mass based off of where this lands. And you also have to calibrate this with different things so you know what those are. But this is the use of a mass spectrometer, because then we can figure out what the mass of that starting material is in order to determine what the molecular formula is from the empirical formula. So here's an example where we can isolate something to the extent of easily between a single atomic mass unit between different elements. So a mass spectrometer is an instrument that we can use to determine the molecular mass. And you can kind of see here, that's what the magnet is going to be deflecting depending on the size. And we're going to be able to, the detector will be down here to tell us what size and charge we're getting out. I mentioned earlier glucose. And we know the molecular mass of glucose is 180.16 grams per mole. We can also get that from the mass spectrometer. So that could give us something, and maybe we don't, it's 180, it comes up as a peak on that mass spectrometer scale, that mass to charge scale I just showed you. So obviously this one only goes to 50, but they can get a lot bigger depending on the model. And so if we were able to identify something with this mass, and we know from combustion experiments that the empirical formula was CH2O, then the empirical formula mass is 30.03. So we can add the 12.01 grams for carbon, the 1 gram per mole times 2 of the hydrogen gives us this number, and then the 16 grams per mole for oxygen to get us approximately 30.03 grams per mole. Now it's pretty simple. All we have to really do is we can take this bigger number, divide it by that smaller number, and then we know the number we need to multiply these atoms with in the empirical formula by. So then we multiply 6 carbons, 6 times 2, 12 hydrogens, 6 times 1 oxygen, and then we get our molecular formula C6H12O6. So this is a way that we can use the mass spectrometry data to look at first identifying the empirical formula from a combustion experiment, for example, and then determining what the actual molecular mass is with a mass spectrometer. So let's practice doing one of these problems. So if I have an empirical formula of a compound is shown here, it's going to be P2O5. If the molar mass is determined to be 283.9 grams per mole, what is the molecular formula? So here we have the empirical mass. And what we want to do then is to determine that number of n that we need to multiply these by. Remember, this is just a ratio. And we're going to just take the molecular mass, which is the molar mass or the molecular mass, 283.9 grams per mole, and divide it by the empirical mass. So we need to determine that. So what is the empirical mass? We need to take our values that were given. We have 2 phosphorus, so that we know that phosphorus is going to be about 31 grams per mole. And we multiply that by 2, so we get 62 grams per mole for that phosphorus component. We have 5 oxygen, so those are about 16 grams per mole each times 5, because we have 5 of them. That's going to give us 80 grams per mole. And we can add those together, 142 grams per mole. So then we would take the 283.9 divided by 142, and that gives us about 2. So now we know we need to multiply the 2 by 2, so that's 4. Oxygen by 2 is 10. So this is the actual molecular formula. All right, I have hydrazine, the mass spectrum. If I put rocket fuel into our mass spectrometer, this is what we would get out. And you're able to actually look some of these up. You can Google search what these would look like, and they're a whole catalog. So even our mass spectrometer, if you put some unknown compound in, it does a search, a database search, and it'll look at different this is kind of the fingerprint of what you'll see, and you'll get that out. So if I put this in, this is what we would expect to see out. The empirical formula of hydrazine is NH2, and its molecular mass is shown below. So we'd have to actually identify, typically this is going to be the largest thing that we see on here. And you'll notice there's another set of these down here. And so what's happening here, these are just some fragmentation off of that compound. So you might have a hydrogen leave. There's some little things that might happen there. You might have different isotopes variants. And this set here is usually because it's taken on an additional charge. So this might be the +1 charge state, and might be the +2 charge state. Remember, it's mass divided by charge. So if the charge is 2, that whole number goes down by 2. So this is usually what we call the parent ion, and that's the one we're going to be looking at. So we see a 32 grams per mole. That's how you'd read this out as what our compound likely is. If we then know that our molecular mass is 32, what's the molecular formula? So you should work through this, look back at the last problem, and see if you are correct. I used to do an experiment where we would take dollar bills and look for trace amounts of different banned substances, and I never found anything really that great. So I'm just going to show you this image of what an example of cocaine would look like if you were to look for this on a $20 bill, for example. This is what you would expect to show up. And notice this is actually the parent ion, that heavy ion that's going to, it's the heaviest thing, right? The biggest mass to charge. But we're not actually, it's not the highest, most relative abundant ion. So this falls apart, these things get clipped off, and then we get higher numbers of hits on the detector. But this is the thing, the top thing that's going to actually define and determine what the mass of the whole molecule is. So 303 grams per mole. Okay, so now that we hopefully have a good feeling about what is a molecule and how those fit together and how we determine those from a chemistry perspective, the next step of this is to look at how do we look at chemical reactions. Once we know what the molecule is and we want to react it with another molecule, how do we interact those, and then how do we make sure they're balanced, and why is balancing important? First off, balancing is really important because when we have a chemical reaction happening, we know one of those Dalton theories of matter is that we can't lose matter. Matter doesn't go away, and at least not typically. And we need to make sure that we're accounting for all of the matter, all of the stuff in the chemical reaction on both sides, in the reactants and the products. In order to do this, the first step is to write the unbalanced equation on the piece of paper, whatever you're looking at, and just recognize what are the reactants and what are the products. And then we're going to use some tools and tricks to adjust coefficients to get equal numbers of each of the different kinds of atoms on both sides. So let's look at some examples for doing this. In the lab, we actually do this. We take hydrochloric acid and react it with zinc, and it reacts to form zinc 2 chloride and hydrogen gas. So we want to write the unbalanced equation from these words, right? So what is the easy way to write this down? So we know we have to start with zinc, and it starts as a solid in this instance. Hydrochloric acid is an aqueous solution. That's what the AQ means. It means that it's mixed with water. So this compound is in water. That's what the AQ stands for. It reacts to form zinc 2 chloride, which is aqueous, right? It's a homogeneous mixture. We don't see that coming out of here, but it's going into the water, and we're not necessarily seeing big chunks of zinc chloride fall off, but it's in this solution. And we also see gas. That's the bubbling. That's the H2. This is unbalanced right now because on the right side, I can just tell you right now, we have 2 hydrogen atoms and we have 1 hydrogen atom. So this is not balanced. This doesn't work. We also have 2 chloride ions and we just have 1 here. So we need to fix that. So let's adjust the coefficients to balance the numbers on each side. And if we take 2 HCl, that fixes our problem. Just as a hint for balancing equations, it's a good idea to try to balance the non-hydrogen oxygen atoms first. So look for, like that last example, not necessarily the hydrogen, but the chlorine. And that one helped us just by addressing that. It fixed both of the problems. Also, it's a good idea to identify polyatomics and balance those as groups as long as they don't change, right? If you add an oxygen or a hydrogen to that grouping, then that's changing it. So if you can identify those, try to identify those as groups, and that will make things easier. So here's another example of silver nitrate, sodium phosphate react to form silver phosphate and sodium nitrate. So here we're going to keep the polyatomics as a group because it's going to simplify our work. So NO3, PO4, we see PO4 over here, and NO3, those numbers, right, those numbers of oxygen don't change. So we can keep those as groups here. I typically like to do some accounting, and I will look for counting on the left side of the reaction and the right side of the reaction. So you can see reactants. I'm going to start with silver and sodium. I'm going to do my non-hydrogen oxygen ones first, and then I have silver and sodium, and you can see right away that there is an imbalanced issue here. So, but we're gonna fix those first. I'm gonna fix that. I'm gonna multiply the left side with this silver. I'm gonna multiply by 3 to fix that discrepancy. And I'm also going to then multiply the sodium over here by 3 to fix that one first. So I'm going to focus on the non-polyatomics first and then see what that does. So now let's check the polyatomics. And here we have NO3. We have 3 of those now on the left side because we've multiplied by 3. And then we have 3 on the right side. So great. We have 1 phosphate on the left, 1 phosphate on the right. Good. We're good to go. The equation is balanced. So here are some practice problems. Do these, bring these to class or post them on Blackboard if I have that option for you. And I would like you to make sure that you can't change the compound, remember. Again, the first step, I think, is to identify polyatomics. So you might want to pull out a list of polyatomics or look in your book. For example, sulfate here, that's a polyatomic. We can see this is outlined already, this OH. Can be defined as a polyatomic. So identify those, find those, put parentheses around those so that you know what is what and that you want to keep those together. And as long as those stay the same, then you can keep those. The problem here, right, you might want to do this as a polyatomic. The problem is that isn't found on the right side. So you would have to break this one apart now. So this is a good place to stop before we start looking at stoichiometry and essentially using these coefficients for these chemicals in order to generate different types of conversion factors so that we can do comparative analysis between our starting materials and our products that we get out.